In this session, we will discuss the periodic trends in the properties of elements in the modern periodic table. The number of protons in an atom is called the atomic number, and the atomic number increases by 1 unit as we move from one element to the other. When the elements are arranged in the increasing order of their atomic numbers, it leads us to the classification known as the modern periodic table. Thus, in the modern periodic table, elements are arranged in the increasing order of their atomic numbers. The horizontal rows are called periods, while the vertical columns are called groups. Thus, in the modern periodic table, the elements are arranged in 7 periods and 18 groups. The group 1 elements are lithium, sodium, potassium, rubidium, cesium, and francium. The electronic configuration of lithium is 2-1. That of sodium is 2-8-1, and that of potassium is 2-8-8-1. Thus, all the elements in the first group contains the same number of valence electrons, that is 1. Valence electrons are the electrons present in the outermost shell. Thus, we can conclude that all the elements in a particular group have the same number of valence electrons. Next, we will discuss the periodic trends exhibited by the elements of the periodic table. For that, we will consider the elements of the first group. They are hydrogen, lithium, sodium, and potassium. Their electronic configurations are also given here. Hydrogen has got only one shell, lithium has got 2, sodium has got 3, and potassium has got 4 shells. Thus, we can generalize that the number of shells increases down the group in order to accommodate more electrons. Next, we will discuss about the atomic size. As we move down the group, the number of shells increases and thereby the atomic size also increases. But as we move down the group, the atomic number increases. As the atomic number increases, the attractive power of the nucleus increases. Thus, according to theory, the atomic size has to decrease. But the electronic shielding prevents the outer electrons from being attracted to the nucleus. Thus, they are loosely held and the resulting atomic radius is large. Thus, the shielding effect, that is repulsion between electrons, is more as compared to the increase in nuclear charge, and hence the atomic size increases down the group. Valency of an element is the number of electrons lost, gained, or shared in order to attain the stable electronic configuration, that is 2 or 8 electrons in the outermost shell in a chemical reaction. For example, sodium with atomic number 11 has got 2 electrons in the first shell, 8 electrons in the second shell, and 1 electron in the outermost shell. Thus, the number of valence electrons of sodium is 1. In the case of chlorine with atomic number 17, it has got 2 electrons in the first shell, 8 electrons in the second shell, and 7 electrons in the third shell. Thus, the number of valence electrons in chlorine is 7. Valency can be defined as the number of electrons lost or gained in order to attain stable electronic configuration. In case of sodium chloride, sodium donated 1 electron and chlorine accepted 1 electron. Now, both has attained the stable electronic configuration. Thus, the valency of sodium and chlorine is 1. We will now find the valency of the following elements. First, in the case of lithium, the atomic number is 3. The electronic configuration is 2-1. For lithium to attain stable electronic configuration, there are 2 options. One is to lose 1 electron and attain 2 electrons in the first shell. The other option is to accept 7 electrons and attain 8 electrons in the second shell. Which is easier? The easier one is losing 1 electron. Thus, the valency is 1. Similar in the case of boron with atomic number 5, the electronic configuration is 2 and 3. For boron to attain stability, 2 options are there. Either to lose 3 electrons or to accept 5 electrons. Which is easier? Losing 3 electrons is easier. Thus, the valency is 3. Next, in the case of carbon with atomic number 6, the electronic configuration is 2 and 4. For carbon to become stable, both options are same. That is, to lose 4 electrons or accept 4 electrons. Thus, the valency is 4 itself. For the first shell to become stable, only 2 electrons are required. From the second shell, 8 electrons are required to attain stability. In the case of nitrogen, with atomic number 7, the electronic configuration is 2 and 5. Here there are two options, either to lose 5 electrons or accept 3 electrons. Which is easier? The second option, that is accepting 3 electrons, is easier. Thus the valency is 3. Similar in the case of oxygen, with atomic number 8, the electronic configuration is 2 and 6. Here, to attain stability, either it has to lose 6 electrons or accept 2 electrons. The second option is easy, that is accepting 2 electrons. Thus the valency is 2. Next, in the case of fluorine, with atomic number 9, the electronic configuration is 2 and 7. To attain stability, it has got two options, either to lose 7 electrons or accept 1 electron. The second option is easy, that is accepting 1 electron. So the valency is 1. Neon with atomic number 10 has got electronic configuration 2 and 8. It has got already the stable electronic configuration. So it need not accept or lose electron. So its valency is 0. On the other hand, the number of valence electrons are 1 for lithium, 3 for boron, 4 for carbon, 5 for nitrogen, 6 for oxygen, 7 for fluorine and 8 for neon. This is how the valency and valence electrons are linked together. Now we will discuss the periodic trends down the group. First, the valence electron. In the first group we can see that hydrogen, lithium, sodium, potassium. The number of valence electrons are the same. Thus, down the group, the number of valence electrons remain the same. Next, in the case of valency, we can see that for all these elements, the valency is 1. That is, 1 electron has to be lost in order to attain the stable electronic configuration. Thus, down the group, the valency remains the same. Ionization potential is defined as the energy required to remove an electron from the outermost shell of an element. As we move down the group, the atomic size increases. As the atomic size increases, the attractive power of the nucleus to attract the outermost electron decreases. Thus, the ionization potential decreases down the group. In simple words, as the size of the atom increases, the attractive power of the nucleus to attract the outermost electron decreases. Thus, the outermost electron can be very easily removed, and hence, down the group, ionization potential decreases. Next property is electronegativity. It is the ability of an atom to attract electrons towards itself. As we move down the group, the atomic size increases. As the size increases, the attractive power of the nucleus decreases. Thus, down the group, electronegativity decreases. Most of the metals tend to exist as positive ions. Examples are K+, Mg2+, etc. The positive ions are formed by the loss of electrons. As the tendency to lose electrons increases down the group, metallic character increases and non-metallic character decreases down the group. Next we will discuss the periodic trends along the period. Along the period, the number of shells remain the same, but the effective nuclear charge increases due to the increase in the number of protons, and thus electrons are very strongly attracted towards the nucleus, and thus the atomic size decreases along the period, except in the case of noble gases. Next we will discuss the variation of valence electrons along the period. For sodium, the valence electron is 1. For magnesium, it's 2. Aluminium 3. Silicon 4. Phosphorus 5. Sulfur 6. Chlorine 7. And argon 8. Thus, the number of valence electrons increases along the period. Next we will discuss about valency, which is the number of electrons lost, gained or shared in order to attain stable electronic configuration. The valency of sodium is 1, magnesium is 2, aluminium is 3, silicon 4, phosphorus is 3, sulfur is 2, chlorine is 1 and argon is 0. So the valency first increases and then decreases along the period. Next we will discuss the variation of ionization potential across the period. Ionization potential is the energy required to remove an electron from the outermost shell. As we move from left to right of the periodic table, the number of protons increases, thereby the attractive power of the nucleus increases. Also, the atomic size decreases along the period. Thus, the electrons in the outermost shell are very strongly attracted by the nucleus. Thus, it is difficult to remove an electron from the outermost shell. Thus, the ionization potential increases along the period. Next we will discuss the variation of electronegativity along the period. Electronegativity is the tendency of the nucleus to attract the electron towards itself. As we move along the period, the atomic size decreases. On the other hand, the effective nuclear charge increases. Thus, electronegativity also increases along the period. As the tendency to lose electrons decreases along the period, the metallic character decreases and the non-metallic character increases along the period.